So we're in section 5.6. All right, so the first thing that I want to talk about is I'm going to call it a property. I guess it's a property of addition and property of numbers. And we're going to need this property when we talk about our inequalities. Our property. So I'm going to say that A, some number A, we get by adding two numbers together. And I'm going to say that C is greater than 0. So we're saying C is positive. Well, if we get A by adding some positive number to B, then A has to be bigger than B. We get A by adding something to a number. So A has to be bigger than the number that we added something to get A. So that's our property. All right. So the first inequality that we're going to talk about has to do with exterior angles. And this is a corollary. And remember, a corollary is just something that we can figure out easily once we already know a theorem. So let me draw a picture so we can remember something about exterior angles. There's our triangle. I'm going to call this angle 1, this angle 2, and this angle 3. This is an exterior angle. And we called these other two angles, angles 2 and 3, were remote interior angles. Remote means they're far away from the exterior angle. Interior means they're inside the triangle. Exterior means it's outside the triangle. And do we remember what we said? I think it was back in might have been back in chapter 3. No, I think it was in chapter 4. Relatively recently. What we said about angle 1 and angle 2 and 3. How does angle 1 and angle 2 and 3 compare to each other? Or what do we do to angle 2 and 3 to get angle 1? Yeah. We add them together. So our exterior angle theorem said the exterior angle is these two angles added together. Well, what our corollary is going to say is the measure of an exterior angle of a triangle is greater than either remote interior angle. So what we're saying here is the measure of angle 1 is greater than the measure of angle 2, and the measure of angle 1 is greater than the measure of angle 3. Well, why is that the case? Well, we know that the measure of angle 1 equals the measure of angle 2 plus the measure of angle 3. And both of our angles are positive. Angle 2 and angle 3 are both positive. We don't have negative angles. Well, by the property that we just talked about, angle 1 has to be bigger than angle 2 because we have to add something to angle 2 to get angle 1. And angle 1 has to be bigger than angle 3 because we have to add something to angle 3 to get angle 1. And the reason we're talking about this after we did a little section on indirect proof is to prove that corollary, you would use an indirect proof or an indirect argument. You would say, well, assume that the measure of angle 1 is not bigger than the measure of angle 2. And then you could figure out that your angles in your triangle didn't add up to 180. So you'd get a contradiction. So that's why we're talking about this right after indirect proof. That's how we prove it, is we assume that it's not true and show that that leads to a problem. All right. Are we good there? All right, let's look at an example of how we might use this. Here's my picture. Call that angle 1, 3, 2, and 4. And we want to know, how does angle 1, I'm going to say how to measure of angle 1 and the measure of angle 4 compare? So we want to know, angle 1 the same as angle 4, angle 1 smaller than angle 4, angle 1 bigger than angle 4. Well, what do we know about angle 1 and angle 2? Which one of those is bigger than the other, smaller than the other? One is bigger than 2, because that's an exterior angle. How about 1 and 3? 1 is bigger than 3. How about 3 and 4? They're vertical angles, so they are congruent. They're the same. Well, if 1 is bigger than 3, what does that tell us about 1 and 4? 1 has to be bigger than 4. And we figured that out by realizing those two are the same, and one is bigger than 3. That's the corollary that we just talked about. All right, questions on that example? Pretty easy idea. Our next theorem, another pretty easy idea. In a triangle, this doesn't have any special name. In a triangle, the largest side is opposite. Opposite just means across from the largest angle. The medium side is opposite the medium angle. And the smallest side is across from the smallest angle. And that makes sense if we think about it. If you have a big angle, to connect the sides of the angle, you're going to need a longer segment. If you have a small angle, to connect the two sides of the angle, it's going to take a smaller segment. So we put those together in a triangle, then we get this relationship. And again, to prove this, we would use an indirect proof. We'd start by, for the first one, for example, saying, well, assume the largest side is not opposite the largest angle. And then you could go from there and figure out that you reach a contradiction. All right, so let's look at a couple of examples using this. This is a nice theorem. When you solve problems in the future, it is important sometimes to know, okay, which is the biggest angle, because that's the one that I need to work with. Which is the biggest side, because that's the one you need to work with. And this is how we're going to be able to choose. So here's my triangle here, and these are not not to scale. All right, so in this triangle, what we want to know is which is the largest angle. All right, so in that triangle, which angle is going to be the biggest? Angle A. A is across from the biggest side, so it's got to be angle A. All right, good, makes sense. Let's look at another one. We can do the same thing with the sides. So here's my triangle for this one. So that angle is 51 degrees, 64 degrees, and 65 degrees. We want the sides smallest to largest. So we want to list them smallest to largest. All right, so what's the shortest side here? And remember, go by what the the information tells you, not by what the picture looks like. AB is going to be the smallest side because it's across from the smallest angle. What's the next one? The medium one. AC is the medium one because it's across from the medium angle. And that only leaves the largest one is across from the largest angle, so that's got to be CB. And I'll put here not to scale. So go by what the information tells you, not by what the picture looks like. Sometimes the picture's not to scale because the problem is trying to trick you. Sometimes it might just be because someone's not great at drawing triangles to scale. All right, questions there? All right, the last theorem that we're going to talk about today. This one is kind of the main theorem of this section. And this is the one that I said is one of the most important theorems in math. The triangle inequality theorem. The triangle inequality theorem says the sum, and when we say sum, what does that mean? What are we doing? Addition. Sum means add. The sum of the lengths of any two sides of a triangle is greater than the third side. So what we're saying here is if we add together any two sides of a triangle, it's got to be bigger than the other side. So on this triangle, I'm going to call this side 1, side 2, and side 3. What the triangle inequality tells us is that side 1 plus side 2 is greater than side 3. Side 1 plus side 3 is greater than side 2. And side 2 plus side 3 is greater than side 1. So you can add the two sides in any any pair of sides and is bigger than the third side. Well, let's take. I'm going to draw some pictures to talk about why that is the case. I'm going to say that's my third side, and there are the other two sides that we're trying to make a triangle out of. Well, if those two sides don't add up to be longer than that side, they're too short. They can't connect up to the end of this side. There's no way we can make a triangle by connecting to that point. These are too short. We could try to go the other, put it on the other side, put one here, and put one here. They're too short to connect. They're not long enough to reach each other. So here those sides are too short. And notice it says greater, not greater than or equal. If the two sides add up to be exactly equal to the third side, I'm going to put them kind of on top of each other here. We get a situation like this. If they're exactly the same and we connect them up, there's not enough space to make an angle. So we just get two segments on top of each other. So we get the same segment. There's not enough space there to pull those up to make a triangle. So that's why it has to be greater than. Otherwise, they're too short to connect, or we just get two segments that we can lay right on top of the third segment, and we can't make an angle. There's not enough stuff there to make an angle. And again, we prove the triangle inequality theorem by using an indirect proof. Start by saying, well, assume that side 1 plus side 2 is not greater than side 3. And then you make an argument that essentially says what those pictures show us. And then you would have a contradiction. You don't have a triangle. The triangle inequality theorem, it shows up in lots of contexts. It turns out that it's true in 3 dimensions or higher dimensions. You use the triangle inequality theorem. It really has to do with kind of the structure of the universe, how the universe works, the triangle inequality theorem. It's a lot of times when we're doing geometry, the stuff we're talking about seems like we're talking about triangles, and that's kind of ho-hum. But we're right on the edge of stuff that's really, really, really interesting. And the triangle inequality theorem gets us right there on the edge of stuff that's really, really interesting. All right, let's take a look at how we're going to use the triangle inequality theorem. One question, one type of question you might be asked is, can we make a triangle with these sides? So for our first example, we have 6, 8, and 13. So we have little segments that are 6, 8, and 13 units long, and we want to know, can we put them together to make a triangle? Well, we need to check our pairs. 6 plus 8 is what? 14. Is 14 greater than 13? Yeah? We're good there. How about 8 plus 13? 21. Is that bigger than 6? For sure. And how about 6 plus 13? 19. Greater than 8. So no matter how we put together the pairs of the sides of the triangle, it's bigger than the third side. So our answer would be yes. Those segments can make a triangle. How about 3, 9, and 12? Well, let's check. 3 plus 9 equals 12. Is 12 greater than 12? No. Not greater than 12. So we can't make a triangle. Because if we put that 3 unit segment on top next to the 9 unit segment, it would be exactly as long as a 12 unit segment. So we could just set it on top. There's not enough space to make an angle. Does anybody see the shortcut we could use here? Yeah? Add the two smaller numbers and make sure that they're bigger than the third number. Because 13 by itself is already bigger than 8. So if we add something to it, or 13 is already bigger than 6, so if we add something to 8, add something to 13, it's definitely going to be bigger than 6. 13 is bigger than 8, so if we add something to 13, it's definitely going to be bigger than 8. So you just have to check the two smallest sides. That they're, add them together and make sure they're bigger than the third side. In this kind of problem. Well, let's look at one other kind of problem, because a lot of times we want a variable in there. We want to know, we don't know the exact length, which we're trying to figure out some information. So we kind of make a connection with algebra. So in that case, you might be asked about you might be given two sides of a triangle. Two sides are 7 and 9. What are the possible lengths of the third side? So we know two sides. We want to know, well, we want to build a triangle. What are the lengths of the third sides that would let us do that? Well, in math, when we don't know what something is, what do we like to call it? X. So let's say the third side is X. And we're going to use a triangle inequality theorem with 7, 9, and X, just like we did in the example before. So from the triangle inequality, we know that X plus 7 has to be greater than 9. If I add those two sides, it has to be bigger than the third side. I can subtract 7 from both sides, and this says X has to be greater than 2. So that one tells us that that third side has to be bigger than 2 to make a triangle. Let's look at second possibility. X plus 9 has to be greater than 7. So those two added together has to be bigger than that side. I subtract 9 from both sides and I get X is greater than negative 2. Can the lengths of the side of a triangle be negative? No. So I'm just going to toss this one out. We can't have negative side lengths. So don't worry about that one. And then we have one other possibility. 7 plus 9 has to be greater than X. When we add those two sides, it has to be bigger than the third. So this says 16 is bigger than X. The other way I could write this, I can turn this around. X is less than 16. So X is bigger than 2, smaller than 16. Because if it gets bigger than 16, then the other two sides, 7 or 9, are too small to connect. So we could say X is between 2 and 16. Any length between 2 and 16 would let us make a triangle. Smaller than 2, it's not going to be able to connect. Bigger than 16, the other sides are too short to connect. And the way we could write this with math symbols is 2 less than X less than 16. And that's from connecting these two. 2 is less than x, and x is less than 16. I'm fine if you say x is between 2 and 16. All right, questions? Okay. All right, so I'm going to answer questions on any questions we have on the bookwork. And I'll answer some questions on the algebra review.